vou fazer uma... Richard, se podemos começar. Okay, good afternoon, everyone. Welcome to another seminar of our cycle of seminars here at the Astronomy Department. Today, I'm very grateful, very happy to present Bernardo Ferreira, our speaker today. Bernardo Ferreira finished his PhD in May of 2025 at the Universidad Federal de Minas Gerais. In August of the same year, he started a postdoc here at IAG-USP under the supervision of Professor Beatriz Barbuy. Bernardo is a member of the VISCACHA Survey, focused particularly on the study of star clusters in the Large Magellanic Cloud. And precisely, he's going to talk about this topic. So, Bernardo, whenever you are ready, you can start.
Okay, thanks. Is the microphone working? Okay. So, hello, everyone. Thanks for the invitation. I'm glad we managed to do this time. So today I'm going to share a little bit of the work we've been doing with VISCACHA in the context of star clusters in the Magellanic Clouds. But before we do that, I'm not sure how familiar you are or not with the clouds. So I would like to start by asking the question of why should we care about these galaxies? Why they are interesting? What do they have that is special? So if you're very unfamiliar with the clouds, you have two galaxies here. The Large Magellanic Cloud are roughly 50 kiloparsecs and with a total mass of 10 to the 11 solar masses. And you also have a companion here, the Small Magellanic Cloud, at around 60 kiloparsecs and with a mass of 10 to the 9 solar masses. These galaxies are actually pretty special. So they are the most massive satellites of the Milky Way, our galaxy. They are also the closest example we have of a pair of interacting binary galaxies. And they've been interacting with our galaxy as well, so they have some appeal from the extragalactic sense, but also in the galactic context. They are also very interesting objects observationally. So as you can see here, they are kind of close to us, and they are not obstructed by the galactic plane, so we can get really detailed observations of them. So here you have an image of the LMC taken in infrared with VISTA. And on this plot here, you have some inset, some zoom-in views of this region where you can see that we can observe these galaxies with great detail and even resolving their stellar populations, which is not something we can take for granted when you're talking about other galaxies. Now, I mentioned that these galaxies are interacting, and how do we know that? Well, one way to look at it is the gas structures which are associated with them. So here in the background, we have an optical image of the sky of our galaxy. And here in pink, you have a density map of neutral gas, which is associated to these galaxies. And you can see lots of structures here. So of course, you have these bright points over here, which are the clouds themselves. They have gas on them. But you also see this structure here that trails behind the clouds, which is the Magellanic Stream, which is gas that is following them in their orbits. You have another structure here, which is the leading arm, which is curious because it is ahead of them in their orbit, so goes in front of them. And so these structures here, the Magellanic Stream can be completely explained through ram pressure, but the presence of the leading arm kind of asks for a little bit of tidal interactions that are stretching this gas. And between the clouds, you also have the Magellanic Bridge, which is a bridge of gas that connects these two galaxies. But even more interesting, it hosts a significant amount of stars. So here is the images here are just a composite image make it from Gaia data. And you can see the star here you have on this plot is showing the position of some stars just to show you that this structure is reaching stars differently than the leading arm and the Magellanic Stream. Okay. The interactions are also imprinted in other aspects of the clouds. So for instance, here we have the star formation rates of the SMC on the top, and in the bottom, we have the star formation rates over time from the two different regions of the LMC, This blue one is the spiral arm of the galaxy. The red one is just a region of similar size, but in the south of the arm. And you can see the star formation rates here. You see that the star formation history of the SMC has various bursts of star formation, and that these bursts actually coincide in the same time than bursts in the star formation of the LMC. And the idea here is that as these galaxies interact, they get close, they get far apart, they can trigger star formation on each other. Another way to look at it is from the structure of the galaxy. So this is an edge-on view of the large Magellanic cloud produced from red clump stars. And you can see that stars kind of fall within a plane, but as we move to the outskirts in the southwest, which would be this region here, towards the SMC, the galaxy warps. It leaves the plane and approaches the direction of the SMC away from us. And here is just a view of the structure of the SMC from classical C-fates. Here older C-fates and here younger. This plane here, the XY plane, would be the face-on view. So here will be the direction of the line of sight. You can see that the SMC is very elongated along the line of sight. And if you look closely, you start seeing some bimodality, some streams, etc., which shows how complex the structure of this galaxy is as well. So, okay, they've been interacting. What is the history of the clouds? There are currently two paradigms to explain that. The most successful one is the first in fall scenario. So here on these plots is the result from a simulation. In the first one, you have the relative position of the LMC in this ugly green and of the SMC in black in relation to the Milky Way. And here you have the relative position, the distance between the LMC and the SMC. So the first in fall scenario predicts that the clouds are long-term binaries. You can see that they've been approaching and departing from each other from a long time, at least 6 billion years. But they only recently became bound to the Milky Way. So you can see here, recently they completed their first pericenter passage less than 1 billion years ago. And as you move past in their history, they just become farther and farther and farther from the Milky Way. So the idea is the opposite, right? They came from very far away and they're just now approaching. There's also another type of model, which is what we call the bound scenario. And here is just the relative distance between the LMC and the SMC in black, and then with the Milky Way in red and green, where the hypotheses are inverted. So the clouds are individually long-term satellites of the Milky Way. So they've been orbiting the Milky Way from a long time, more than 6 billion years. But they only just recently became binary. So if you look at the relative distance between each other, as we move past, they were far away and just now became interacting with one another. So you can see that you cannot have both. They cannot be long-term binaries and satellites of the Milky Way. Regardless of the scenario, we know that these galaxies have been experiencing close encounters. So you can see a very close recent event, less than 300 million years ago, which is believed to have formed the bridge, and also a second encounter between 1 and 2 billion years ago. So later developments kind of favor the first in fall scenario. You can think about the galaxy that the LMC that has 10 to the 11 solar masses just recently completed its first pericenter passage. This is likely to leave some imprints in our galaxy. And two of them that I'm going to cite is a displacement of the center of mass of the Milky Way. So this was predicted in theory by this paper in 2015. And in 2021, Peterson observed a relative velocity between the inner disk of our galaxy and different tracers of the outer halo. So between the center and the outskirts of our galaxy, there are different tracers here. So K-giants, blue horizontal branch, satellites. Doesn't really matter. The most important thing is that there is a non-zero velocity between the two of them. And also, this passage disturbed the distribution of dark matter and stars in the halo of our galaxy. So here is the data that we have. You can see density perturbations kind of. So red is more density, blue is less density. And here is a simulation in the first in fall scenario, where you see that it kind of matches the overall structure. Now, things are never easy with the simulations. You can tweak some parameters, and bound scenario simulations are still done to this day. So you can see the simulation that is very recent from Vasiliev, 2024, where they managed to reproduce these density perturbations in a simulation that is bound. And so here on this plot, you're just showing some Cartesian coordinates. You have the Milky Way and the LMC here. And you can see different orbital histories from different simulations. So this is the Vasiliev simulation. It is a bound simulation. And you have several other first-in-fall simulations here. And what's interesting is this pink region here. This is an observational constraint to the velocity, to the position of the clouds in the past 800 million years, done by hypervelocity stars. And you can see that the Vasiliev simulations kind of pass right in the middle. So they are getting some things right. Which is not to say that the first-in-fall simulations cannot do that. We have this L21 simulation here from Lucchini, which also does the same. It passes right in this region. So hopefully I was able to convince you that these galaxies are interesting. There are still so many open questions about them. Even the more fundamental questions are still being debated today. But then I promised to talk about star clusters and how can they help. So I know this is an astronomy department. I think you all know some star clusters. So I'm going to give you a very simple and biased view of them, just for my interest in me in this sense. So star clusters are a group of stars that form kind of around the same time from the same molecular cloud, and that remain gravitationally bound along their evolution. And what does this mean in practice is that they share many astrophysical properties. So because they form from the same cloud at the same time, they have kind of the same age and the same metallicity. And since they are clumped together, they are bound, they share the same distance, they suffer the same extinction, and they have roughly the same kinematics. And from the photometric side, that is very interesting, because one of the things that we love to do with photometry is determine some colors and some magnitudes to build CMDs, color magnitude diagrams. In the case of a star cluster, since the distances and the extinction is the same, we can say for sure that magnitude differences are differences due to luminosities. And color distances are differences due to differences in effective temperature, log G, etc. The important thing is that the differences are not from relative parameters, they are from physical parameters of the stars in the cluster. So the color magnitude of a star cluster is a distribution of intrinsic properties of the stars in a population that has the same age and metallicity but different masses. And so you have the whole history of star evolution. So if you have a young star cluster, for instance, what do you expect to see? You expect to see the more massive stars falling in the main sequence, and at some point the low mass main sequence stars still getting there. And as they evolve, the low mass will start to settle in the main sequence, and the high mass stars will leave the main sequence and start forming, some structures that we are familiar with that we like to see. And since we have that, we can use stellar evolution models to characterize these objects, which is the famous method of isochron fitting. So you have the models, you find the isochron that better matches your data, and then you can determine the ages, metallicities from the isochron shape. And by varying the whole position of the isochron, you can determine the distance and the color axis. So this wealth of information is really valuable to apply some constraints to the galaxies in which the star clusters are in, which we have many examples in the Milky Way. So here is just an example of young open clusters whose distances and ages can be determined, and you can use them to trace the spiral arms of the galaxies alongside the other star-forming sites. And on the direct opposite, you have some old globular clusters. So this is the age metallicity relation of old globular clusters. You can see here that different clusters kind of follow different age metallicity relations, and this has been used to constrain the assembly history of our galaxy, with some clusters belonging to the original progenitor of the Milky Way and other belonging to satellites that were accreted by our galaxy. Now, to the clouds host a very large system of star clusters, over 3,000 star clusters distributed in the LMC and the SMC together. And so if we apply the same principles, what can we learn from these star clusters? Now, before we get too excited, it's not any kind of observation that we can use for the Magellanic Clouds. These are extragalactic objects. So we need data with sufficient resolution. So here are two star clusters in the Magellanic Clouds. What we see here is that this can be very dense objects. Clusters are clumped stars by default. And you have these galaxies which are far away, so they tend to become, the angular sizes tend to decrease even further. So you need good resolution if you hope to detect the stars in the center of the cluster, particularly the less bright stars. And you also need depth, because to do hydrogen fitting, we need to get the main sequence turn-off of your population. And so this plot here is showing the magnitude of the turn-off as a function of age for a distance roughly of the LMC. And you can see that the turn-off has magnitudes in V between 21, 22, 23. So you probably need to get that depth with good signal-to-noise ratio if you want to determine ages. So these are all things that we must keep in mind. So several ground-based surveys have been trying to observe the clouds, have been observing the clouds in the past year. So in this plot here, you have many of them, some which were done in 2-meter telescopes, other in 4 meters. So the x-axis here is kind of the limiting magnitude. So here would be, you can get really dim stars, and here you can only get the brighter stars. And on the y-axis, we have the resolution. So ground-based surveys are limited by seeing, so the resolution stays around 1 arcsecond, sometimes a little bit better, depending on the atmospheric conditions. And so here would be the best resolution possible with a point size, a PSF. Now, from space, what can we do? We have Gaia. Gaia has great resolution. However, it does not go very deep. It reaches a depth similar to 2-meter telescopes, so you cannot get those CMDs to the turn-off of the older populations. The best data that we actually have comes from the Hubble Space Telescope, which does the best in terms of resolution and age currently. However, Hubble is a highly competitive instrument. It is not a survey facility, so we cannot cover the whole clouds. So we only have data for around 100 star clusters. You can see their distributions here. They're kind of biased towards the center of the galaxy. So you can kind of see where our niche is, right? In that sense, to explore a little bit of this vacuum here and here in the outskirts, the VISCACHA survey was created to observe star clusters in the outskirts of the Magellanic Clouds with the SOAR telescope. It is a 4-meter telescope, so it gets good depth. However, it is a ground-based telescope, so how can we improve that? Well, in SOAR, you have SMC, which is an adaptive optics imager who corrects a little bit of the atmospheric distortions to increase the resolution. And with that, occupying this unique position in the resolution limiting magnitude diagram, let's put it like that, and using a facility that is very less competitive than Hubble, we managed to observe 300 stars focusing in the region, star cluster, sorry, in the region that Hubble doesn't cover over the past 10 years. So a little bit more about VISCACHA. The name is inspired in a little bunny thing that lives in the region where the SOAR telescope is located, in Chile, in Cerro Pachón. It has members in several countries. Most of them are from Brazil, Chile, and Argentina, and many of the other members came from Brazil, Chile, and Argentina. So it is a 4-meter telescope, and this is what we get from adaptive optics. So these are two imagers that we have in SMC. SOI is no longer active. But this is an image of the same cluster without adaptive optics and with adaptive optics. And you can see that the images become sharper. You can get the cluster centers better. You can get more stars. And here you have a comparison. These are all CMDs of the same cluster, here from VISCACHA, here from SMASH. SMASH is a 4-meter telescope survey. From the Blanco telescope, it is a very similar site, but it doesn't have adaptive optics. And each CMD here shows regions closer to the cluster center. So you can see that in the outskirts, we are kind of the same. But as we move to the very center, if you don't have adaptive optics, you lose the less bright, the dimmer stars. And that's a shame because the center of the cluster is exactly the region where most stars are. So okay, what can we do with that? So we have 300 star clusters observed with data that I promised you, which is great. So what can we do? Well, First thing, the images don't come ready for us to use, so we need to get the images that come from the telescope and produce measurements of positions and magnitudes. So this is done with the pipeline developed by Professor Francisco Maia, which is currently a professor at Federal do Rio de Janeiro, but who did a postdoc here at the Institute. So he has a crowd field photometry to the pipeline to get those measurements. And then we want to look at the stars which are from the star cluster. But when you observe a star cluster, you have stars from everything. So from the field and from the star cluster itself, we cannot have good proper motions from Gaia to perform this cleaning process. So we have to use kind of a photometric approach, which is also a code developed by Francisco. Essentially, you separate the region of the cluster and the region of the field. You look at the CMDs, and the idea here is if the field is homogeneous, the presence of the cluster will produce some overdensity in this inner region. And so you compare the number of stars and you get membership probabilities, and you can see how important this is for this cluster, because if you look at the original CMD, this is where the turnoff would be, and after decontamination you can see that it's not, it's here. So this is really important for our characterization. Now you need to do the high-score fitting. There are several approaches to this. Even VISCACHA is not homogeneous, but I want to share a little bit of my work. So in my PhD, I worked to develop the pipeline to perform this type of fitting. We don't use only the isochrone, but we actually do what we call synthetic CMDs, which is to add a couple more ingredients to produce a more realistic distribution. So first, this is a isochrone in the dotted black. So the first thing we do is we sample realistically some stars using the initial mass function from Krupa. You can see that by doing that, we have stars which occupy the main sequence, the clump, but the other regions not so much, which is what you would expect. Then we add some binaries, because that's inevitable. You always have some non-resolved binaries, no matter how good the resolution is. Then we actually remove some stars, because the clusters will not follow the Krupa IMF due to incompleteness of the sample or other dynamical effects. And finally, we add noise proportional to the actual errors of the observation. And so we can get these cluster-looking CMDs here, which we then use all the same things, Markov chain Monte Carlo, Bayesian theory to compare with the data. And then what we get is these probability distributions of each parameter, which we can use to get the final values of age, distance, metallicity, and color axis. So here's just the final result. In orange, you have the observations. In green, we have the synthetic data. You can see that they match quite well. And I'm just telling you that because CS is a public tool. So if you do CMDs, you can come talk to me, and we can discuss if that would be useful for you. Now, let's talk about science, real science. I'll start by talking about the work of Rafael Oliveira, which did his PhD here at IAG, but is now at University of Warsaw in Poland. So what did he do? He looked at 33 clusters in the Magellanic Bridge. So this will be the SMC, and this is the clusters he analyzed. So the first thing, these points here are colored by their ages, and the green arrow kind of shows the position of the age of the bridge. Remember, the bridge was formed in the latest close encounter between the clouds. So all these purple points here are older than the bridge. So they were not there when the bridge, they already existed before the bridge was formed. So they were stripped, likely from the SMC. And then you look at the age-metallicity relation, just focus on the yellow points, you can see a strong dip in metallicity around 1 billion years ago, which is roughly the timing of that other collision that I just mentioned. And it is also a dip that is older than the bridge itself. So I'll come back to this in a little bit, but I want to talk about the work of Sarun, which is a PhD student. He just recently completed his PhD in Chile. And he looked at clusters in the SMC outskirts as well. This is the sample that Sarun worked. This is the bridge that Rafael worked. And he did the same thing. This is the age-metallicity relation of the bridge. He combined some clusters from the literature. And what you see is that the chemical enrichment history, the metallicity increase, drops, and then increases. And this drop in metallicity is associated with a major merger that the SMC experienced 6 billion years ago. The idea of a merger is not new. It's in other chemical enrichment models from the past years. But they use this to calibrate the ratio of mass between the two mergers. And also, by looking at how the metallicity increase and associating that with starbursts, they reconstructed a star formation rate for this region, which is also quite bursty. You have peaks of star formation that increase the metallicity. Now let's look at the works of Sarun and Rafael together. So this is the bridge clusters Rafael analyzed. This is their age metallicity relation. This is the clusters that Sarun analyzed, and in blue here we have the age metallicity relation. So this blue line is the model that they fitted, and you can see it here near the bridge. And this red line is just the fiducial line between the clusters from Rafael. And you can see that they're very interesting, very different. So the bridge clusters apparently did not felt the metallicity reduction due to the merger. And at the same time, it's not clear if the SMC clusters experienced this metallicity dip, which is kind of amazing because the bridge didn't exist when those things happened. So theoretically, all these clusters were together and then they were stripped. So it's a very complex scenario. Now, what about the LMC? The LMC was the subject of my PhD. So I looked at 85 star clusters around the LMC. This is their distribution here. The colors indicate the position angle. And you can see the age metallicity relation here. So we don't see major variations in the age metallicity relation as we saw with the bridge and the SMC. It kind of follows the same thing. It kind of traces nicely this chemical enrichment model here, which is a very classical model from the 90s. And if you look at the age distribution as a function of this position angle, we can see some behavior. So in the north, this region here, you have many ages. Young clusters with 3 billion years around this age. But in the southwest here, the ages are actually very concentrated in 2 billion years, which probably ties to the star formation history of these regions. And finally, here I just compared the age metallicity relation of the LMC, the bridge, and the SMC. And you can kind of see a dip here at the same epoch of this dip. So probably it is kind of expected, since if these galaxies experience a close encounter around this epoch, whatever produced this dip could also be the same region that produced this one. Now, if you were paying close attention, you notice that all of the clusters I presented to you are younger than 4 billion years. So is this some bias? Are we missing old clusters in the LMC for some reason? And not really. So the LMC has a very interesting feature, which is the age gap. So here you can see the age-mass relation of LMC clusters, and here you see the age-metallicity relation of LMC clusters. So you have a group of 10 to 15 massive, old, metal-poor clusters, which are very similar to our own globular, galactic globular clusters. And then you have this group of clusters around minus 0.4 in metallicity and younger than 4 billion years. And between there is a gap. So this is just the cluster frequency. And you can see the gap here where the frequency of clusters drop to 0. So in this log scale graphs, it doesn't seem like much, but it is an interval between 4 and 10 billion years. So it's 6 billion years of very few clusters being formed in the LMC. Amongst the known age gap clusters, in the past you only had 3. One that was discovered in the late 80s, and 2 that were discovered very recently in 2022. You see the ages here. And then you have a discovery by Gato 2024, but it is using very shallow survey. Those would be newly discovered clusters. So these are not confirmed as real clusters right now. They are cluster candidates. But with VISCACHA, we are actually able to detect an age gap cluster, so which is the cluster SL2. And this is the CMD that we have. So in gray, you have the actual observations, and you can see the best fitting model here in green. So you can see that we get the turnoff, we get the red clump, and we get an age of 7 billion years. So this would be the fourth age gap cluster, but it doesn't appear on those previous plots because of the range of the graph. And it will be very silly to extend so much for a single point. Now, we can get cluster distances as well. It comes from a parameter of the high-score fitting. And what we decided to do was to look at how these distances change in our clusters. So here you have a face-on view of the LMC, and the colors here indicating that position angle. And here you have a distribution from the distance to the plane of the galaxy of each cluster as a function of this position angle. So you're kind of wrapping around the galaxy. So remember that I showed you a warp in the southwest of the galaxy. That would be this structure. You see the cluster distances increase, reach a maximum, and then decrease. To facilitate the comparison, this is an edge-on view of the galaxy from the field stars and here from the clusters, and this would be kind of the warp behavior here on both plots. But we also notice that the clusters have a very vertical structure in the outskirts, with many of them being closer to us than the galactic plane. And finally, this point here, which is outlined in red, is the age gap cluster, and you can see that it kind of follows nicely the structure of the warp of the LMC. So moving towards the end here, what else can we do with these clusters? Well, I've been showing you the same technique over and over again, high-score fitting, high-score fitting, high-score fitting, but you can do other things with clusters, and actually you can look closely at the clusters themselves. So Stefano Souza, which also did his PhD here at the Institute and is now at the MPIA in Germany, he looked at a phenomenon of the main sequence, the extended main sequence turnoff. What is that? Well, essentially it's a phenomenon in which the turnoff of clusters have a larger dispersion in color and magnitude than what you would expect from synthetic populations. Here's just an example. In orange, you have the observations, and in green, you have a synthetic model. This model has binaries, so it's not just a matter of missing binaries. And you can see that the dispersion of the turnoff here, from what it is observed, is larger than what you would expect from a single stellar population. A very likely explanation is the presence of rotating stars. So here in black, you have a 2 billion year non-rotating hydrochrome, a model without rotation. And the colors here show a model with rotation. And once you have rotation, the stars are no longer spherically symmetrical. You have a dependence of the inclination between the inclination angle and the line of sight. And the stars become brighter on the poles. And that naturally creates some dispersion in the turnoff. And that's not even accounting for different rotation velocities. So only a single velocity can produce this effect. So it's a very likely explanation. So what did Stefano do? He looked at VISCACHA data, searching for clusters with extended main sequence turnoff, and determined several parameters. I'm just showing you here the width of the turnoff as a function of the cluster mass. And you can see that it kind of follows a linear relation. The VISCACHA data would be these highlighted points. And the same relation is observed in more massive clusters that were only observed before with Hubble. So we are showing that we can do that with ground-based telescope and with less massive clusters. There's also the work of Professor João Francisco. He was my PhD supervisor, and he works at the Federal de Minas Gerais, and he looked at the cluster structure. So here are the clusters he analyzed, here in the LMC, here in the SMC. What he was looking at is the density distribution of stars as we move radially away from the cluster. So the density tends to decrease, and you can fit models to that. He used the simple King model, which has a core radius, a tidal radius, which gives you the cluster size. And the core radius and the tidal radius define how concentrated the cluster is. What did he find? Well, this is the distribution of clusters in of the tidal radius, the cluster size, in the LMC and in the SMC. In gray, you have a previous catalog of more central clusters. And in green, you have the clusters he analyzed, which are in the outskirts, and they tend to be larger. the potential of the galaxy is smaller in the outskirts, so you kind of tend to have larger clusters. We see that in the Milky Way as well. And here we are looking just at these clusters from the LMC. So we have the position angle here and all structural parameters fitted. And you can see that in the southwest, the cluster structural parameters become more dispersed. So we are seeing some kind of thing that is perturbing these clusters. Probably, these clusters have all kind of 2 billion years, as I showed you. So you have these collisions, you have the warp. These things might be disturbing their structures. So finally, a little bit about spectroscopy. We have an initiative which is led by Professor Bruno Dias. He did his PhD here, but he's a professor at UNAB in Chile. You have Professor Matheus Ângelo from Cefet, Brazil, and you have Professor Celeste Parisi from Argentina, which they all join forces to send proposals to Gemini, which is a joint consortium between these three countries and the US and others, to do a spectroscopic follow-up of VISCACHA clusters, specifically using GMOS in the Gaussian triplet limit to determine metallicities and radial velocities. So let me just show you an application of that. So this is a study led by Bruno Dias. He was looking at these clusters here in the northern outskirts of the SMC, sorry. So this is the bridge, and this is the region Rafael studied. Now you're here. And what he did was combining VISCACHA, Gaussian triplet, and average Gaia proper motions to get several parameters. So here is the position of the clusters, and here you can see their distances. They're actually heliocentric distances from high school fitting. And here you can see the position and radial velocity and total velocity, distribution. So you see that we have these red clusters here, which are closer to us, and they are all moving from the bridge towards the LMC. This is what you would expect from the typical bridge cluster. But you also have this very interesting purple cluster here, which is much more distant than the other. And it is moving back to the SMC, And so this was identified as a counter-bridge cluster. The counter-bridge is predicted from models, which would be a counterpart of the bridge that is warping around behind the bridge and coming back to the SMC. Now, we've been doing this for over 10 years, getting this data. What does the future hold for us? Well, lots of more data will come from new surveys. So we have LSST, which in time, when the images stack together, you have great depth. The resolution, we don't really know, doesn't have adaptive optics. So observations will be scene limited. Maybe then can combine just the best nights to get amazing resolution. Maybe not. So it's a bit of a mystery here where we will land in terms of the limiting magnitude resolution diagram. But we have very exciting space-based missions, which is Euclid from ESA and Roman from NASA. Roman just completed the call for proposals yesterday, I think. And they promised to deliver high-quality data, Hubble-level quality data, for a wide region of the clouds, because those are, differently from Hubble, survey telescopes. They can cover a very large area. So this is really exciting. Rubin, of course, as well. It has time coverage, but I'm a little bit biased towards those. And not to mention, you have Apogee, you have LVM, which is the local volume mapper. You have formals coming from the spectroscopic size, and we also have future data releases from Gaia, which can only help. Right? So a lot of new data is coming. So some take-home messages. I hope to have shown you that the Magellanic clouds are a very interesting environment. You have many open questions, many things to explore, and you can get amazing data for it. It's very different from other galaxies in this sense. You can get high-quality data, Milky Way comparable data for the clouds. Star clusters are very powerful tools to constrain the galactic structure and evolution. And that the future will bring a lot of data, so we have plenty of reasons to be excited and ready for that when it comes. That's it. Thank you.
Thank you very much. Excellent talk. So let's start with the questions.
Very interesting talk. I have a curiosity about the clouds because both are very massive, have satellites, but I don't know anything about if they have satellite galaxies around them. You mentioned several stellar clusters around, but could some of them be considered satellites in the sense of satellite galaxies?
There is, I didn't put here, but there are some plots that show when you look at this very faint, ultra faint, very faint galaxies. Some of them are very biased, very close to the position of the clouds or their past orbits. So it is believed that the Magellanic clouds can also have, particularly the LMC, which is the very massive one, can have its own little system of satellites, which it brought with it when it entered the Milky Way potential, if you're talking about the first impulse scenario. Along these clusters that I've been showing you, no, most of them, go back.
They are young, you know.
Yeah, the very old globular clusters, they would be in the Milan work. Let's see how much I have to come back here. I think this is it. So not all of these clusters are very old, but they would be alongside. So we have some weird clusters very far away. I'm not sure of their ages, which could be. There has been talk about some globular clusters here being accreted, but not necessarily the galaxies of them. But these galaxies have a system of faint galaxies which are nearby them. Yes, they do.
And do the Large Magellanic Cloud have a massive black hole at its center?
It's believed to have one, and I think it's not an active black hole, it's not an AGN in any measurement. But people with these hypervelocity stars are starting to trying to find it, trying to constrain the position where here this cluster will be, because we cannot do these things that we do for the Milky Way to get those full orbits. But now people are really starting to look for them. So in 2024, 2025 papers.
Okay, thank you.
Bernardo, very nice talk, very nice review. I see that you are an expert in Magellanic clouds. Okay, so I have a question regarding, you know, putting these clouds in a broader framework, because, you know, James West space telescope has observed, you know, galaxies at very high redshifts, and there was this surprise with the, you know, of objects that shouldn't be there. Yeah. And now there are these claims that, you know, to try to understand what is going on, why those objects are and how they are formed, because they were, some of them were not expected in cosmological simulations. You didn't expect those objects shouldn't be there, right? Mm-hmm. And now people are looking at the interactions, exactly the outskirts of several of these objects, right? To understand, to try to understand the evolution, galaxy evolution, in a broader context, looking at the interactions with the immediate environment. So in this sense, these clouds and their interactions, you know, with the Milky Way, all these processes, so my question comes, to what extent you would expect that the Magellanic clouds could be a proxy for these, you know, for these investigations at cosmological level of galaxy evolution, looking at this environmental interaction.
I'll be talking very far away from my comfort zone here, but the first thing is that they show is how modeling these interactions can be complex. So you have a very simple system, LMC, Milky Way, SMC, and even right now, people have been discussing whether these galaxies were always together or not. So it already shows how complex these things might be. And I think as we move forward with data and, for instance, coming Roman and everything, people are expecting to be able to use the bar tilt of the LMC to apply some constraints to the mass of the SMC and whatever. So I think once we are able to kind of solve this first conundrum here, which is, are they really a long-term, are they really infalling in our galaxy? Could these recent bound scenario models be the reality of these clouds? I think once we are able to do that, we can start talking about new tests. Because, for instance, if the galaxies came from very far away, then you have some new questions of where they formed, and you can talk about this idea of groups of galaxies which eject a satellite and then another one accretes. Right. So it's a very hard interaction history. I'd say that the clouds have always the best shot for us to be able to get the very best simulations, the very best data. So I see that in that sense, but the exact details, I'm not sure how they could contribute.
Right, but anyways, you have such amount of rich data. Yes. That I think you can build a scenario and make, prediction for
the most recent simulations.
Galaxy evolution.
You can, so especially when talking about elasticity and particularly those space telescopes, I would expect the simulations to really improve in that sense, that you can really constrain the structure. And to the point that right now we talk about exploring, for instance, with apogee, people explore stars that were stolen from one galaxy to the other by looking at differences in abundance gradients, etc. So I think you have a good chance of having this laboratory where you have a very good understanding of the interaction history.
Right. Thank you.
Okay, I have a question myself about your work on the small cloud. You mentioned that there was this age gap in the clusters. First, a naive question, I would guess is related to the star formation in the galaxy. And can you relate this stop of star formation with some of the interactions that you mentioned through the history of the galaxy?
Yeah, no, that's a great question, and you can already see on this plot here that between 4 and 10 billion years ago, which would be the gap of the LMC, the star formation rates were very small. So this is something that you can already grasp, and that's the simplest explanation. So star formation rates are very low. You can only form a few clusters, and these clusters were very less massive than the other ones that you formed in the beginning. And so because they're less massive, maybe they suffered more dissolution, and so you have even fewer of them today. So that's the current explanation for the gap. There are some interesting things about it, all of them which you can accommodate in this explanation. So for instance, one thing that we see about the gap is that the age gap clusters are only found in the outskirts, which is okay. The very crowded regions, it's hard to find a faint old object with very few stars, so that would be easy to explain. But you have these types of things. So the thing that we hopefully we will be able to do with these amazing surveys coming up is to have a census of the actual number of age gap clusters, to the point that you can start to compare with the star formation rates and see if they are consistent. So are we missing clusters? Or even more interesting, do we have a surplus of clusters maybe that could be tied to stolen clusters from the SMC, for instance? that's something that probably we'll be able to get in the future.
I see. Okay. Thank you. More questions? No? Okay, let's thank the speaker again. Many thanks. And we can meet during the coffee break.